Let me put the recording. Oliver, this recording is just for your presentation about the model which you have prepared, Hudgkin-Huxley model. And yeah, we are here for you. Let me know, what do you need then? You want to share your screen with us?
Yes.
Yeah, guys, thanks. And guys, the others, Mingji, Sean, Linda, and Brian, you also look and you also pay so much attention to Oliver presentation because it helps you also to shape your own presentation when your presentation is due by next week. Then make sure you ask questions. Okay, Oliver, you can share your screen and we can't wait to hear you then, man. Good luck.
Okay, can you see my screen now?
Yes. Oh, that's a beautiful screen. What was that symbol? What was that cartoon iconic?
Which one? Oh,
The one on your
the
desktop.
wallpaper?
Yeah,
Actually, I don't know what is that.
it was so beautiful. Yeah, please go on.
So, hi everybody, I'm Oliver. Today I will talk about a perfect mathematics model in biology, Hudgkin-Huxley model. Hudgkin-Huxley model is a mathematical model that describes how action potentials in inner system are initiated and propagated. The Hudgkin-Huxley
You mean
model was
propagated, huh? You means move along.
yes.
Propagated. That's right.
The Hudgkin-Huxley model was published by Alan Hudgkin and Andrew Huxley in 1952. They received the 1963 Nobel Prize in Physiology or Medicine for this work. In 1952, people's understanding of iron channel is based on very simple basics. There is an iron going through, similar to the discharge of capacitor, but the relationship between voltage and current is not a linear relationship. So Hudgkin and Huxley realized that ion channels should be both dynamic and steady condition. How to describe this complex dynamic process? The genius of Hudgkin and Huxley is to borrow the principles of thermodynamics. They first assumed that the conductivity of an ion channel depends on the difference between inside and outside of cell membrane. Since the conductivity and ions concentration are related, then the distribution of ions should be follow Boltzmann's principle in thermodynamics.
Sorry, Oliver, which principle you said? It should follow which principle?
Boltzmann's
What is that? How do you spell that?
Bultmann.
Oh, Boltzmann. That's right.
Yes, Boltzmann.
Boltzmann principle. It's something in. Do you know what is that?
Uh, Not really, because it's
No.
about dynamics.
No
I
worries.
heard this
No
far.
worries, Oliver. It's gonna be a homework and the next presentation topic then. Boltzmann principle. Okay, sorry for interruption. Please go on. Can you read back again from the Boltzmann principle?
Okay,
Thanks.
so because uh, the conductivity and concentration are related, so this relationship should follow Boltzmann principle in thermodynamics. So based on that, Hudgkin and Huxley established this circuit model as shown at this. In addition to the mean sodium and potassium ion channel, the current through the chloride ion channel is written as IL Lie current. Therefore, the expression of total current through cell membrane can be written as this, as
Can you
shown.
go back to the previous slide?
Oh wait. Yes.
Thank you. This is extracellular medium, both an intracellular medium, and you have this, I should say, circuit, which is, can you explain what is that?
So this basically is like 2 test points. So, they create a model to find out the relationship between the current and the conductivity.
Uh-huh.
So basically it's like that, yes.
Okay. Nice. Yeah, please go on.
So the relationship can be written as this. So from that we can know that also the electric current of each ion can be written as here as shown. And the key point to find the electric current is the openness of ion channel. So basically it's the conductivity, because the openness of ion channel is related to voltage and time. We can write the conductivity as G ion equals to f of Vm comma T times G ion. G ion is the maximum conductivity. So f of Vm comma T is the equation. Here is the equation for ion channel after experiment and analyze. Hudgkin and Huxley came up with the following differential equations. So it's all the equations here. In this equation, m and n are the dimensionless quantities, which
Sorry,
are
what is dimensionless quantity? What?
which one?
You said that something is a dimensionless quantity.
Yes.
What is that? What item is a dimensionless quantity?
The m, n, and h, they represent.
Okay.
Yes, they are dimensionless quantities which are associated with potassium channel activation and sodium channel inactivation. I represent the current per unit area. R for I and beta I are rate for the ion channel. So respectively, R of I and beta I take the form like this one. In the original paper by Hudgkin and Huxley, the function alpha and beta is given by this. So they model the alpha and beta to evaluate the voltage gate channels. The equations are fed to voltage claim data briefly. When the memory potential is held at constant value, for each value of membrane potential, the nonlinear gating equations reduce to equation of the form of this. Thus, for every value of membrane potential Vm, the sodium and potassium current can be described as this here. In order to arrive at the complete solution for the propagated action potential, one must write the current term I on the left-hand side of the first differential equations in terms of V, so that the equation becomes an equation for voltage alone. The relationship between I and V can be written from cable theory, and it's given by, can you see here? Yes, right corner here. So the relationship can be written like this. Where A is the radius of the axon, R is specific resistance of X polarium, and X is the position along the nerve fiber. Substitution of this expression for I transform the original set of equations into set of partial differential equations, because the voltage become a function of both X and T. Well, the original experiments treat only sodium and potassium channels. The Hudgkin-Huxley model can also be extended to account for other specific of iron channels. So this is my presentation. Thank you. Thanks for listening.
Oh, fantastic, Oliver. That was mind-blowing. Fantastic, man. Fantastic. Thank you very much, Oliver. Thank you. It was brilliant. It was brilliant. Guys, anybody has a question? Sean, Mingji, Linda, Brian?
No question.
Mingji, you have a question, you said?
No question.
Sean, Brian, Linda?
No question, teacher.
How about you, Sean?
Nope.
No. How about you, Brian? Okay. I just, Oliver, it was a brilliant job, but I have a question to ask from you. Can you please share your screen with us again?
Yes, sure.
Thank you.
Yes.
You talked about on the previous slide, you said that you talked about the existence of the partial differential equations. Can you go back to that and say that again once more? Which one is a partial differential equations, and what is the significance of that thing? What does it mean?
So the differential equations, because we need to know, we need to have a complete solution for the propagated action potential. So because we know that one side must be the current I, and the other side is the equation, the first differential equation in terms of V, so that the equation is only about the becomes the equation of voltage alone, so it's only related to voltage. So because the cable, from the cable theory, we can know that the relationship between I and V can be written like this.
That's right. And that's fantastic. And the last question which I have, look at those three questions, and everybody listen to that. You have three equations on the very top, M and H and N, all of them as a function of time, which it's represented by an exponential decay function. You see that the e to the power minus t over a constant which is called tau m, tau h, and tau n. What, guys, first of all, you will see here the thing which we talked about that before. And Sean, look at this one. That's what you may need for your mathematical modeling challenge next week. Look at this one, Oliver, that you got those ones very beautiful equations. 1 minus e to the power minus t divided by a constant, tau. And that's an exponential decay. What is this? What is the meaning of that? What is decaying there, Oliver? It seems that something is being decayed. What is m, for example? What m measures? M of t, m function of t with respect to what?
MOT is the function we use to evaluate the voltage gate channels.
Voltage of the gate channels, and then what is H and what is N?
HN are the dimensionless quantities associated with potassium channel and potassium channel activation and sodium channel inactivation.
Okay, and are they decaying with respect to the time because you use them? The persons they used, I should say, some kind of exponential decay function to represent that. You see that e to the power minus t divided by a constant tau. What is decaying there? It means that the voltage with respect over the time it's decreasing, or that's what it means?
Yes.
That's super,
Yes.
man. I really like that presentation, and it was so much things to learn. And Oliver, what do you think? I think there was lots of things that you learned also from that presentation. There was lots of
Yes.
very advanced stuff.
Yes. It's
Yes.
hard, but I learned from it.
Yeah, it was, to be honest with you, this is a so hard concept in the whole science, and that's why it won a Nobel Prize in physiology. In what was the date? 1968? What was it on the first slide?
1963.
1963. That's right.
Yes.
That's man. Congratulations, Oliver. You worked on something so hard that it won a Nobel Prize in physiology. Fantastic, man. It was brilliant. Thanks a lot, Oliver. Thanks a lot.
So can I stop sharing?
Yeah, please. Thank you. Okay, and now, guys, also, it was our first presentation by the model of the Hudgkin Huxley, and over the next week, some of you also guys have the same presentation. And then let's see. I can't wait to hear and see all of your presentation. And thanks again, Oliver. It was a brilliant presentation. I really enjoyed that. Thank you. Okay.